to introduce Colin McClarty, who's talking about Galois theory in PA and EFA, elementary functional arithmetic. Colin.
I'm really happy to be doing this. You know, I'm not acculturated in arithmetic, so I'm afraid I'll say some things that need to be said, and I don't know. I'm kind of hoping that some of you might have some ideas about some of it, but I'm hoping on the other hand you don't already know all of it. What I've been working on, this is towards getting a first order proof of Fermat's last theorem. I don't care that it actually be written in first order, but an articulate argument that we really can prove Fermat's last theorem in Peano arithmetic. I believe we can. I was working on a project that I think we can, but I would like to articulate it and really be able to say. And what got me started on this was Rivet's theorem, which is about odd continuous representations of the absolute Galois group of the rationals. Now, being a continuous representation means that it's really a representation of the Galois group of some algebraic number field. That's what continuity here means. It means it factors through some finite Galois group. But to be odd means it takes every complex conjugation to -1. And so how do you describe complex conjugation on the Galois group of an algebraic number field? I mean, you sort of know what it should be, but can we do this in a first order characterization? Looking at how to express Galois theory in first order arithmetic, you see that the subject is very close to the arithmetic. That's just the way it's normally done. It is naturally close to the arithmetic. But to do this, what we have to do is we have to get rid of, we have to not refer to the absolute Galois group. We have to not talk about embedding algebraic numbers in a complex plane, because you don't have a complex plane. Now, for lots of purposes, you didn't want this anyway, a just straightforward textbook Galois theory. But to do it all without this, so far as I know, I don't know where it's done. I would relate this to, well, three other kinds of work. Well, just computational algebra. It's possible that everything I want to know is already known to experts on SAGE. But SAGE is extremely complicated. I haven't been able to dig it out of there. SAGE has lots of, I mean, I just mentioned SAGE, it could be any number of these things, mathematically, lots of them. SAGE has lots of executable Galois theory. Now, if it's executable, it's pretty much got to be in Peano arithmetic. And so it is. The problem with this literature, from my point of view, well, two problems. This literature is extremely concerned with feasibility. And feasibility is a huge and difficult subject that's not a concern for my project. And so, obviously, a lot of the time is taken up on that. The other is that this literature is not concerned with how you verify correctness of an algorithm. It's not a joke, it's a very serious point to say. I mean, right now we have an extremely simple algorithm that searches for solutions to the Fermat equation. By Fermat equation, I just mean a to the n plus b to the n equals c to the n. We have a very simple algorithm that searches for all solutions for this in all exponents greater than 2, which is alt. This algorithm searches for all the solutions. Now, this is not a self-certifying algorithm. This is not an algorithm that, well, what the computer scientists call a self-verifying algorithm. You wouldn't know from this algorithm that it was correct. But you do know from current proofs that this algorithm is correct. And this literature isn't concerned with how you know things are correct. So even though, in some sense, this makes all the Galois theory, it puts it all into Peano arithmetic, so to speak, it doesn't necessarily put the verification of the claims about it into Peano arithmetic, because they don't care how the claim is verified. They say, this finds all the solutions to the Fermat equation. But you wouldn't know it just to look at this instruction. Another thing I would compare it to is Angus McIntyre's CDM. CDM. Well, and it's not just McIntyre's, it's Sherlin Van den Dries McIntyre, which is why it's CDM. This associates to every field, actually every field, a model structure, a multi-sorted model structure, where a first-order multi-sorted language can essentially discuss all the Galois groups over the field that you put in. And so it's a structure that deals only with finite Galois groups. You interpret it in a first-order language, you get information about the absolute Galois group, about the union of all of the Galois groups. Well, not the union, the colimit, right? Because this is when you combine them, you keep track of all the relations among them. The CDM method certainly goes to show that a lot of Galois theory can be expressed in first-order terms, but it's a model theoretic technique. You give it a model of a field. So, for example, you give it a model of the rationals. As model theory per se, it doesn't care what axioms for arithmetic proved what property. You give it a model of the rationals, and it will give you back all the arithmetic that was implicit in whatever theory you use to discuss that model. There's no provability in the CDM method. So, I mean, what model of the natural numbers did you have? Whatever model of the natural numbers you put in, you do put one in the sense that you put in, well, you might not only be applying this to the rationals. I'm interested in applying it to the rationals. But it's not, there's no provability predicate in the CDM method. There's only registering the information that's in the model. Now, everything you know about the model you deduced somewhere. And you could say, look, everything expressed here, you can now formulate it in Peano arithmetic. Well, I shouldn't even say formulate in Peano arithmetic, because Peano arithmetic is an axiom system, not a language. You can formulate it in the first-order language of arithmetic. But the system, this model theory doesn't care. Well, I mean, I'm not sure people getting what I mean to say about this.
When you say models of the theory of the rationals, are you talking about other models of the first-order theory? I mean, or in a specific signature? Or,
No,
or you just mean the rationals somehow in isomorphic fields?
Yeah, you could take the rationals. You can actually begin with any field, but this is a field specified as a set, not a field axiomatized in some theory. So when I specify that I've got naturals, and from them I've got integers, and from them I've got rationals, and now I'm going to apply this to the rational field.
So you don't have any non-standard models?
Well, I could put a non-standard model in if I want to.
Okay.
But my point is this method doesn't care. This method doesn't deduce things from axioms. It just registers whatever I put in. If I put in a standard model, it will reproduce standard truths.
Well, that's right. I mean, so if you haven't put in the theory, then there's not really a sense in saying it applies to non-standard models because you haven't specified non-standard models of what well-known first-order theory. So you just put in some structure and you get out some...
Yeah, and showing that you can prove something here doesn't mean you can prove it in Peano arithmetic. If you code up consistency of arithmetic in these terms, which I suppose you could do, maybe it's not attractive, you could do it, this will return that arithmetic is consistent because you've really put that into your Q. Unless you wanted to use a non-standard set of naturals that codes an inconsistency proof, and then this will report the inconsistency proof. This is not sensitive to what kind of model you put in. You have to put in a model. You can't say, now you could do meta-theoretically, you could say, I'm going to pursue the CDM method, but in my meta-theory I'll only use statements provable in primitive recursive arithmetic. But this method doesn't care you said that. That's just up to you to have said it. So you might as well just work in, for this purpose, this method doesn't really advance you much. I will say that studying this method is what got me doing the work I'm doing. But you quickly see that the method isn't reflecting any kind of provability relation. It's just giving you back what you gave it.
Can I ask a stupid question? What is that method?
Oh, yeah, like you take Q. Okay, yeah, it's worth saying. you take some field. Let me call it K. You take a field K. You want to do Galois theory over K. What is an algebraic number over K? Well, an algebraic number over K is a polynomial, say degree n, which is just a set of n elements, of a list of n elements of K. You just, now, if I want to regard this as a degree n polynomial over K, I know how to add and multiply polynomials. And I could code add addition and multiplication of polynomials this way.
But you get all the roots at the same time that way. How can you code add this root of this polynomial to some, well, what does this mean? This doesn't mean anything. But
because the great thing about Galois theory is that an element of a degree n extension is just an n tuple. It's not an equivalence class of n tuples. You can do an element. So an element of the algebra of the number field defined by this is some n minus 1 tuple. Well, I mean, how do you count it? I mean, you know.
Oh, maybe I'm asking a question. Are these? Well, should I think of these the coefficient of the polynomial, or are these coefficient, or are these coefficients given some basis for the? So
no, these are coefficients of the polynomial.
All right. So plus. So you haven't given anything to tell us the difference between plus I or minus I. It's just that there's two of them.
Right now, all you know is that you know the degree of the polynomial. You know what its coefficients are. You also know that okay. Now you've got a canonical primitive element for this extension, just the variable of the polynomial. This is just the Kronecker construction. You know that in that base, an algebraic number has just one less coefficient than you had before, and you know how to add and multiply these.
Right.
You can interpret arithmetic in the extension.
Okay, so that's what the B's are coefficients
Mm-hmm.
given some basis with, yeah.
Yeah, well, the canonical basis, the Kronecker basis. This is a polynomial in X. You just take polynomials in X modulo this polynomial in X. And that's what's great then is you know a basis for that. So now we can talk about the theory of algebraic numbers in this field, but further, because all the field automorphisms are given by an action on the base, they're all finite objects too. You can code up all the automorphisms. You can interpret Galois theory in this, you can interpret the Galois theory, the Galois group, you can interpret the Galois group of this extension in the first order theory of K. Better than that, you can interpret the Galois theory of all extensions of degree n uniformly in the first order theory of K. You can interpret the Galois theory of all extensions not uniformly, because your coding has to reflect the degree of the polynomial. So you can do the whole Galois theory of a field in first order terms, so to speak, but not uniformly in the degree of the field. Uniformly over any bounded degree, but not uniformly in all degrees. So now you can take a lot of Galois theory, and most things you want to know about the absolute Galois group of your field really do come down to quantified statements about finite Galois groups.
Mm-hmm.
So you can do all of this.
But that quantified statement for all n might well be something which is quote unquote true, but not necessarily provable in PA.
Well,
right?
so
that's the issue.
We can't quantify over degrees here.
Right.
For a given n, we can quantify over extensions of that degree, or even extensions of that degree or lower. But we can't quantify by this method over the degree of the extension.
Right. I mean, not directly, but there could be a context, for example, if you're working over a decidable theory, there could be a context where any given one of those could be translated into some statement in arithmetic, and then you'd have an actual out and out pi 1, 0, is that the term?
Yeah, you might. Now, the truth is, where this method has worked is for, if I'm not confusing quasi and pseudo, for quasi-algebraically closed fields. Unless it's pseudo-algebraically closed fields.
What is quasi?
Quasi is...
Which is the one we like?
What Angus works on,
They're, okay, I know the characterization that comes out of it. They're the ones whose infinite Galois groups are free projective. That's a lot to ask of a Galois group, that it should be free projective. And this is what got me started, because the point of this, okay, so this method really isn't meant to work over Q. This method was not invented to be useful over Q. It was invented to be useful for other problems. Now it does formally. You can apply it over Q, but it wasn't invented to be useful over Q. And when you look at it, we're missing something really important when we work over Q if we use this method, which is that even if you looked at Peano arithmetic, in Peano arithmetic, we can code all degrees uniformly because we can code finite strings. So we didn't have to say that a degree n polynomial was an n-tuple. We could have said a polynomial is a finite string, any length finite string. And now we can quantify uniformly over the lengths. So for purposes of exploring Fermat's last theorem, you really don't need this kind of apparatus. You've got better available already because you're really working over the natural numbers. And what that suggests, of course, is if the point of this is to code things up as strings, then you would naturally, at first, you don't want to look at Peano arithmetic. At first, you want to look at elementary function arithmetic. Which is sometimes called exponential function arithmetic. And I prefer calling it exponential function arithmetic at first, but then I think it speaks to people more if you call it elementary. What elementary function arithmetic is Peano arithmetic, but in the signature where you have 0, you have successor, you have plus, times, and you include exponentiation in the signature, so you now have a constant for exponentiation, and it doesn't matter, you could have just had exponentiation of 2 if you wanted to. And we take the Peano axioms with the exception that induction is for bounded formulas. Now, am I missing a nuance in calling those delta naught formulas? Delta naught formulas in this language. That's right. Bounded formulas in this language. So, when Hilbert gives his example of what he means by finitary arithmetic, and he wants to be very careful, Hilbert talks about Euclid's proof of the infinity of primes. And he says, if your claim is every n is smaller than some prime, he says this is not really a finitary statement because it doesn't tell you how far you have to search. But when you say it's smaller than some prime, smaller than n factorial plus 1, now you've made a finitary statement because now you've said how far you have to look. Now, Euclid's own proof warrants you in adding this. But he says, to be quite clear, if you hadn't said this, you wouldn't have made a finitary statement. The idea with elementary function arithmetic is, here go iterated, any expression in this language, basically iterated exponentials. Well, this is less than an iterated exponential bound. I don't remember the bound offhand. Or, I mean, there's lots of them. I think 2 to the 2 to the n, and maybe you should add 1 here or something just to take care of the low cases. Yeah. Yeah. So this is an exponentially bounded statement. This is an exponentially bounded quantifier. I did discover when you talk with computer scientists, they say that's not an exponential bound, that's an iterated exponential. And for feasibility purposes, that's a very important distinction. But for the theoretical purpose, it's not. Harvey Friedman, I think, deserves credit. He certainly takes the credit. He deserves it. For saying the point of elementary function arithmetic, this is the weakest arithmetic that gives a natural theory of finite strings, a well-behaved theory of finite strings. And it certainly does give a well-behaved theory of finite strings. And that's what we want to do Galois theory. That's what we want to be able to talk about algebraic extensions of the rationals. We want to be able to talk about finite strings of rationals. In terms of what it is to work in exponential or elementary function arithmetic, one thing that I wonder if people here might know substantially more than I do about and be able to help me with is these exponential bounds. Most often when we invoke an exponential bound, it's going to be concerned with coding rather than with the algebra itself. The growth rates that Galois theory suggests aren't exponential themselves, except when we're coding strings. How do we code a string? Well, we use the Ackermann coding, where any number codes, well, I'm going to write least significant digit first. A binary number. So this is getting greater as we go that direction. This codes the set. The 0th power of 2 doesn't occur. The 1st power of 2 does. The 2nd doesn't. The 3rd doesn't. The 4th does. The 5th doesn't. The 6th does. The 7th and 8th don't. The 9th does. So this number codes this set. So then the union of two sets is like addition but taking care with carry. The intersection of two sets is like the other part of carry, I don't know. This gives a nice theory of finite sets. What does it give? Well, it gives an empty set. Here, I guess, actually, I would like to call up what I've written because I'm not sure I'll do it right off the top of my head. Okay, well, obviously, it gives extensionality. Two binary numbers are equal if they accrete at every place. It gives the empty set, pair set, sum set. It gives power set. I mean, you take the power set of a finite set. Each of those things has a code, and then you just string those out. But this is where, so coding here, we're taking exponentials up here. It gives comprehension for bounded formulas. Any bounded formula defines a set. That's sweet. Well, of course, what you don't have is anything like infinity. But you've got a very nice theory of finite sets.
So are you iterating this, like Ackermann coding all the way down, or are you just doing one level?
All the way down.
Okay.
But that does have the consequence that you can't tell what, given a number, you don't know uniquely what set it codes. You know what set of naturals it codes.
Right.
You also know what set of sets of naturals it codes. If you're told what rank of set you want, a homogeneous rank of set, then you know which one it codes. But if you weren't told what rank, well, it codes sets at many ranks. I mean, is this a code for this 4-element set, or is it a code for the set of four sets, namely the set coded by this and the set coded by that?
Well, that's what I meant by all the way down. I mean, you could decide that to do that all the way, and then you're just recovering finite set theory.
Well,
without any particular.
Well, yeah, I'm allowing you to go all the way down, but what this does mean is when I say consider this set, you have to ask me, did you mean this as a set of naturals, or a set of sets of naturals, or perhaps a set of sets of naturals? So so over and over again in our coding, we have to specify what kind of thing we were talking about. But the coding does work with that specification. And another nice feature here, in our induction, we only allowed induction over bounded formulas, but the natural set theoretic formulas are bounded. When we want to say X an element of Y, we want to talk about all sets that are elements of a set Y. We do know that, I don't have a notation for the code of X, so I'll just write this. The code of X, if X is going to be an element of Y, the code for it has to be less than the code for Y. The code for X is the log base 2 of the code for singleton X. And the code for a set is always less than the code of any larger set. So this is a bounded predicate. When we spell this out in our arithmetic terms, it's a bounded predicate in arithmetic. And over again, the set theoretic properties that we want are bounded in the arithmetic. So we can do induction on set theoretically bounded. You can do then the usual construction of however you want to do. Integers as pairs of natural numbers, rationals as pairs of, well, what, any integer and any non-zero natural number. You can do that usual arithmetization of integers and rationals with the nuance that now when we talk about bounds, this is something that took me a while to get used to, so I'll mention it. If we want to say there exists a rational R, which is equal to rationals Q plus S, this has to, we don't need a magnitude bound on R compared to Q and S. We need a bound on the code for R compared to the codes for Q and S. The code for a rational number is going to be, all codes are natural numbers. Everything in this world is a natural number. This is an interpretation in the language of arithmetic. So if you're talking about m over n as a rational number, well, that's sort of an ordered pair mn, where this is an ordered pair AB of naturals. Maybe you could say that's a natural. If we're going to use the Kuratowski coding of ordered pairs, there's sets down to some level here. They're coded by exponentials to those levels. So we're iterating exponentials as many times as we're ascending in rank in sets. So the code for a rational is a fairly large natural number. Oh, when I say fairly large, what I mean, even if it was a simple natural number, even if it was simple rational, like 3/2, we're probably dealing with 2 to the 2 to the 5th to code this thing. It's not important that we are, but you have to know that you are when you're setting these bounds. And that's going to come up, for example, in Sturm's algorithm. If we want to talk about separation of roots in a polynomial, well, it's this again. I'm not so acculturated to this, so I'm not sure how obvious this is to people. But a very small rational number is going to have a very complex code. The smaller the natural number gets, the higher the code is going to get. So you have to make sure that things aren't shrinking too fast. Because what you need to bound is the growth rate of the code for it. Well, you can in the Sturm algorithm make sure of that, but you have to check that. All of the kinds of things that you would like to be able to do, you can use the Kuratowski ordered pair, and then since you've got finite sets, you can code n tuples for any length n out of those. Again, always saying, well, to put it in terms of rationals, you need predicates like x is the rational sum of rationals y, and z, these are the kind of predicates you're going to be dealing with, because as codes, these are just three natural numbers. And this one won't look like the sum of those two at all. So your predicate has to say, I'm treating y and z as rational numbers. I'm looking for the rational number that's the sum of them. Because they say these will also be natural numbers. These two natural numbers have a sum, but it's not going to be the code for the rational sum at all. And then you start doing Galois theory, and everything moves very smoothly, as you would kind of expect it would. I was hoping this had already been done, not by the people at Sage, because I can't read what they write. But I don't think it has. But a polynomial is a finite string. Once you know the polynomial, the elements of the algebraic number field it defines in the canonical base for the primitive element specified by that polynomial. I mean, I have no idea, for all I know, that that has some integer factorization. But what I do know is, if you want to look at the rationals, if you want to look at the algebraic number field over the rationals defined by this polynomial, you know what its elements are. They're polynomials this long. And you know what their sum is, because it's just the ordinary sum as polynomials. To find their product, you have to know that the remainder function exists here. But the remainder function is clearly bounded over and over again. To work in elementary function arithmetic, basically the difference from primitive, I guess it's easy to start by talking, what is it to work in primitive recursive arithmetic? Every time you want to say something exists, you have to give some primitive recursion that puts an upper bound on it. You have to be able to bound it. Basically here, to show that, if I want to show that greatest common divisors exist, I have to show that calculations of greatest common divisors exist. I have to show for any polynomial and another, and I want to find the greatest common divisor, there's a sequence of polynomials that ends up with their greatest common divisor. And here, it's good enough to show that each step is well defined and that it terminates. Here, it's not good enough to show that each step is well defined and it terminates. You also have to say that each step is subject to a bound you can give before you've taken it, and that it will terminate in a number of steps that you can specify before you've begun the calculation. You can't just say, well, keep track until you've fallen below something or other and then stop. You have to be able to show before the calculation is given that it will stop in some specified number of steps. And that specification has to be in this language. It has to be an exponential specification. Yeah?
I'm a bit puzzled. So, from the description you've just been given the last couple of minutes of EFA and PRA, they sound like varieties of constructivism, but from what you said before, you didn't say anything about not allowing it through the middle. It was all about restricting induction.
Yeah.
So, what can kind of resolve my confusion there?
Yeah, there's no question of excluded middle here. I think excluded middle simply doesn't arise here. I think it wouldn't matter if I rejected it.
It's the complexity of the statement that you're proving.
Yeah.
If you're only proving some statement of pi 2 or pi 1 statement, it's essentially constructive. But when you start looking at pi 2 or pi 3 statements that get through, you find non-constructive aspects.
Yeah. And this is fine with non-constructivity. What this is saying is, you can't ask me to do a calculation that you can't give an exponential bound on its complexity for. Like Hilbert's demand. Hilbert says, don't tell me that every number has some prime greater than it, because I don't know how far you're asking me to look. But if you tell me n has some prime greater than it, but less than 2 to the 2 to the n, now I know how far I'm going to have to look. Now I'll accept that.
But that isn't a demand that a constructivist would impose?
No.
I mean, this, for example, this argument about whether Markov's principle is constructively legitimate, isn't it about precisely this point about whether it's it's enough just to say that there exists something and therefore you can just keep trying until you get there, or whether you actually need to have some bound in advance. I mean, and people normally, I've heard that discussion in the context of whether Markov's principle is constructively legitimate. So that's what makes me feel. That's what made me feel that this was an issue of constructivism.
No, it's not meant to be an issue of constructivism. It's to me what motivates this is an issue of, it really is an issue of complexity. When number theorists say, well, of course Fermat's last theorem can be proved in power arithmetic, I feel like it can. What is it they're feeling? I want to say this is the kind of thing they're feeling. They're feeling that not only is this all somehow finite calculations, it's concretely finite calculations. You know that nothing is too complicated. And so one way to explicate that is people say, well, Galois theory, it's all very concrete. They don't say it's constructive. I've never had a number theorist tell me the Galois theory is constructive. It's just not a thing that I've heard come up. I mean, if I had other conversations, of course it would, but not in these ones. What they say is, don't ask whether that can be done in PA. It's so concrete, of course it can. Well, what does concrete mean? I want to explicate, and I'm happy to agree with them. I say, okay, I'm sure you're right, but I'd like to be able to say it clearly. I'd like to be able to say what that means. And one candidate for what it means is that in Galois theory, you always have these kinds of exponential bounds. Very much the kind of bound Hilbert specified is what he wanted to make himself feel happy. It's a bound on complexity. It's not a constructivity thing. But when you put these kinds of bounds on complexity, do you still get in higher quantifier complexity, right? Because we're not bounding depth of quantifier complexity, we're bounding growth rates. Are there still issues of constructivity?
I'm not sure.
My feeling is
there will certainly be equivalence, a conservation result between EFA and a version like Heiting arithmetic for elementary functions. There will certainly be a conservative conservation result for pi 2 or something. And beyond that, there will be some weird things that you can say that you couldn't say for the constructivist wouldn't be happy with.
Yeah, and that's just not something I've looked at all, because constructivism is not an issue for me here.
But it's always the balance. When you're working with these systems, it's always getting the balance right. All the time. About checking balance all the time. You spend twice as long checking balance if you do any work.
Yeah. And as far as you're doing your basic Galois theory, the bounds, you do some work to show there's a bound. What you don't need to do is worry that it's an exponential bound, because by the time you get at least as far as I've gone, if you get a bound at all, it is exponential. You don't have to take care to make it exponential. And this is what makes me think that even the use of exponential bounds, at least for the parts that I've succeeded at with so far, it's a coding issue, it's not intrinsic to the algebra. The algebraic growth rates aren't even close to exponential, but their codings are. So I'm not sure if you can really make sense of that distinction at all, because algebraic number fields are interpreted in power arithmetic through this coding. I'm not sure you can separate the issue and say, well, what if it weren't for the coding? Well, if it weren't for the coding, that wouldn't be a question. But then I kind of wonder if maybe you could.
But then Hilbert's point was that the bound tells you when you can stop. But if you died before then there's no point. It doesn't help you because it's exponential. It's infeasible.
Well, Hilbert on the infinite is not concerned about feasibility of bounds. He's trying to say, what should we count as finite arithmetic? And I'm willing to be instructed on this by someone like Wilfried Sieg. But to me, when I read Hilbert's German, he's not saying finitary or finitistic. He's just saying finite. These issues have not come to him yet in the way that we see them now. He wants to know what is finite arithmetic. And he says, well, it's finite if I can put this bound, and it won't be finite if I can't put this bound. Even though the next prime after n, it'll be a finite number, but I won't count that existential claim as finite unless you can tell me a bound on how far I'll have to look. Well, what happens here is, okay, now once you've got algebraic number fields, an inclusion of one field in another, okay, so the algebraic number fields here, these all come as quotients of the rational polynomials by some polynomial. This is how we code algebraic number fields, which means that an algebraic number field comes with a selected primitive element. Now that doesn't get rid of the primitive element theorem. The primitive element theorem now says that if I were to take an algebraic number field and talk about its algebraic extensions, those will all be algebraic number fields. Today we say if you give me an algebraic number field with 2 generators, I can get one with a single generator. On this coding, an algebraic number field doesn't have 2 generators, it's got 1. But the content of the theorem remains. If you now define something over this, you get another thing of this form. It's the same proof as the usual primitive element theorem. Now that, so a map from this to another one, which I'll abbreviate K, is just it's just an element of it's just the image of the primitive element. So these maps are all finitely coded. So and a Galois group, and you easily show, okay, a map is subject to a polynomial condition here, which means Galois groups are all finite. Well, but you already knew the Galois groups to be finite, but I'm just saying that it gets represented easily in this coding. So now we can talk about the Galois group of the algebraic number field defined by any polynomial. I mean, what really exists in this is all natural numbers, but then polynomials are n tuples of natural numbers, and so are elements of this. The fundamental theorem of Galois theory, that subgroups of the Galois group correspond to subfields of the field, and that normal subgroups correspond to normal subfields. This is provable here, again, over and over again, well, with bounds. So I had to show, suppose I took this thing and extended it by a new variable, and then modded out another polynomial in x and y. The primitive element here, I need a bound on the code for the primitive element for this whole extension in terms of the codes for these polynomials. Oh, I wish I had not named that the same thing. This is, I don't know, some other polynomial. The code for the Galois group is bounded in terms of the code for the polynomial. All of these boundings exist. I will tell you where I run into a problem for right now. What is a real algebraic number field? Well, any field, a field, is real. Some people say formally real. Yeah. No sum of squares is -1. What I cannot do right now is put any kind of bound on the terms you would have to consider. I do not claim this is a hard problem. I'm not adept enough at this field to be saying something's a hard problem. It's a hard problem for me. I don't know how to bound what kinds of numbers you might have to consider. Because to say in this language, there are no x, y, z, etc., whose squares sum to -1, I can't do induction on that formula unless I can bound the x, y, and z.
If your field isn't algebraically closed, do you want to say it this way? I mean, I'm wondering, like, could you also...
I've got no algebraically closed fields. I've only got finite fields.
But I mean,
finite extensions.
It seems to me that there might be a distinction between -1 being a sum of squares and -2 being a sum of squares, unless you know that. I mean,
no, the proof is very easy that this is just the same as not everything is a sum of squares.
Okay, and that doesn't require algebraic closeness.
No.
Okay.
No. That just requires dividing.
Okay.
So elementary function arithmetic, it's not that a formula has to, it's not that we only have bounded quantifiers. We don't only have bounded quantifiers. It's not that the quantifiers in a theorem all have to be bounded. It is, though, that the quantifiers in a formula we're going to use for induction have to be bounded, which means most of the time, I mean, there's not a lot of use for theorems with unbounded quantifiers in them. There's not a lot of use for definitions with unbounded quantifiers because you can't use them in inductive arguments. Right now, I can't put bounds on these. The direction I would look there is Sturm's algorithm, and I just haven't succeeded in doing a lot with it with the Sturm algorithm yet. Sturm's sequences are easy to define here. Given a polynomial, I can get a sequence of polynomials more or less by Euclid's search for the greatest common divisor between the polynomial and its derivative. This is typical of working in EFA. How do I know that given two polynomials I can calculate their greatest common divisor? Basically because each step, the degrees keep dropping, the coefficients likely become more complicated, but I can put an a priori bound on how fast any of them can become more complicated before I've seen what some of the intermediate steps are. And so I can prove there will be a sequence calculating the greatest common divisor. I can prove there will be a sequence calculating a Sturm theorem, a Sturm sequence. I don't know yet that I can state that I can prove Sturm's theorem in EFA because every textbook treatment I've found of Sturm's theorem uses an algebraic closure. I expect I can. I really think, maybe I shouldn't say I expect I can. I expect you can. Are you going to work on this? I expect somebody could. I wish somebody would. Otherwise, I will. This is the kind of thing that I've come to. Now, the Sturm algorithm, it lets you separate roots of polynomials. What it's going to do is, given any polynomial, it's going to give me a Sturm sequence, and I can then, okay, from a polynomial, I can tell you I can bound its largest and smallest real root. It's easy to, basically you drop all the terms that aren't of maximal degree, if it's an odd degree polynomial. And you put this coarse bound, you say, all the real roots have to occur in this interval. That part can be done with exponential bounds. Sturm's theorem lets you tell how many roots are in a given interval. Well, you can cut this as small as you like until you've separated all the roots. So this means I can give you rational numbers that separate all the real roots of any given polynomial. I can tell you the number of real roots, and I can give you rationals that separate the roots. Well, for this to be bounded, again, it has to be bounded in complexity, but the computer scientists, the computer people, have found bounds on these complexities. It's not hard to compute what's the smallest difference there can be between two real roots. So that you can do. But I was hoping to be able to tell you I've done it all. I haven't done it all. But I take it can be done. It's possible that once I know the Sturm theorem of real roots, then I can put a bound on these summands. For right now, I don't have a bound on these summands. Now, to prove it in Peano arithmetic, I don't need that. So I can state the Artin-Schreier theorem. Okay, what does the Artin-Schreier theorem say? Okay, the